Good morning, all you earth science wonderful kids. We're going to be talking about rocks today, and let's get into it. All right, rocks. Rock is a naturally formed solid piece of the Earth's crust composed of a mixture of minerals. It takes a bunch of minerals to make rocks. Do all rocks have minerals? Well, kind of depends on who you're asking. For example, I have a rock here that is made of glass. This is obsidian, volcanic glass. Well, glass is really not a mineral. It has none of the things that it really requires to be a mineral. It is solid because it cooled so quickly, but the atoms never had time to form crystal patterns at all. So, is this a rock or is it something else? We won't spend a lot of time fussing over that. It's supposed to be composed of a mixture of minerals, and almost all rocks are composed of a mixture of minerals, but you may meet some rocks that push the definition a little bit, and that's fine. So if it contains one mineral, if it's all the same mineral, it would be called monomineralic. This, for example, is a sedimentary rock known as limestone. It's made completely of calcium carbonate, calcite. So it would be monomineralic. Most rocks, however, like a rock like this, you could see is made of many different minerals. That would be called polymineralic. You can see all the different colors there. They're all different minerals. Now, key understanding, geologists are not crazy about rocks per se. What they want to study is what happened here. How did the Earth get to be the way it is? Where's the evidence? Well, think about it. What evidence will the human race leave on this planet that you might discover a billion years from now, or somebody might discover a billion years from now? Where would the evidence be? So much will have changed on the planet that you're not going to find much evidence. So, what's the stuff that would hold evidence? And that would be rock. In the rock that's being made today, you would be able to record some of the evidence that the human race was here. This is one of the first people to start understanding this. This is James Hutton. He is considered to be the father of modern geology. Way to go, James. What did he do? Well, the story of James Hutton is a lot like the story that you and I would have, right? Um, we understood at that time that sediments are laid down one on top of another. If you look at this sedimentary rock, you see a bunch of lines in it. Can you see the lines in that sedimentary rock? All right. All those lines are the sediments being laid down, and they're laid down horizontally in flat beds, one on top of another. How long does that take? How long does it take sand to turn into sandstone? Well, nobody really knew, but they figured it would take a while. At the same time, the modern, or for that time, the understanding was that the Earth was 6,000 years old. Now, that doesn't sound correct, but is that a scientific statement? It absolutely is. Because to be a scientific statement, all you need to do is be something that can be proven wrong. So back to James Hutton. He's out with his dog Missy near on Scotland, near the coast of Edinburgh, Scotland, and he gets to a place called Sicker Point, and he notices something. He sees a bunch of sedimentary rocks standing up straight. So they had to have been laid down flat, turned into rock, and then rotated sideways. But more than that, they were cut off at the top, eroded down, truncated, and then the whole section of the sedimentary rock with the beds all up and down went back underwater and had new rock deposits on top of it. Again, sediments that had turned to stone. 6,000 years? He's right away thinking, no, something like this would have taken much, much longer to occur. So Hutton was the first one to start coming up with the idea that the Earth must be vastly older than we supposed. Way to go. So James Hutton came up with the idea of uniformitarianism. And all that means is that the constant slow processes we see made the Earth as we see it today. The constant slow process, what are they? Well, think of a big storm. Um, that happens pretty often. Does it cause the streams to turn brown? Yeah. What are they filled with? Well, filled with debris. Is that making the valley a little deeper, a little bigger? Yes, absolutely. It's taking the stuff away. So just add enormous lengths of time to that, and you could see that's where things happen. So uniformitarianism, you already know, he's saying, you already know the processes that make the Earth the way it is. You see them all the time. All you need is enormous amounts of time. So we say it this way: the present is the key to the past. The present is the key to the past. And that's the understanding of modern geology. So there are three rock types: igneous, sedimentary, and metamorphic. We don't care what a rock looks like, we care how it formed. So if it was once molten, or from sediments, or recrystallized, they will form the three different rocks. So once molten, igneous. From sediments, sedimentary. And if it's recrystallized from previous rocks, where they recrystallize but never get hot enough to melt, that would be metamorphic rock. Let's talk about igneous rocks. Here we see igneous rocks in the process of being formed. So you could go someplace on the planet today and see igneous rocks being made. So when you reach down in a place that had igneous rocks in it, and you pick up an igneous rock, you can tell that it's igneous because you could have been to a place, or at least read about a person who's been to a place where they saw this rock actually form right in front of them. So igneous rocks form from the cooling and solidification of molten rock. Any rock that is formed this way is considered to be an igneous rock. So watch our graphic here. The magma goes up and bursts through the top. So let's consider the stuff under here. How is that going to be different from the stuff up here? Well, the stuff down here will cool slowly. And if it cools slowly, what will happen? Well, very simply, it'll form very large crystals. On the top, where it's in contact with the cold Earth surface, it'll cool fast. And if it cools fast, it'll make either very small crystals or it'll make foamy rocks with no crystals at all, glassy rocks. So we'll have this either large crystals down here or small crystals up here. So there we go. Intrusive or plutonic form from magma inside the Earth. They have larger crystals and a core structure. Extrusive or volcanic form from lava outside the Earth, smaller crystals and a finer texture. So putting it all together, very simply, if a molten rock cools fast, the crystals do not have time to grow large. Small crystals cooled fast near the surface, large crystals cooled slowly deep underground. And so just by looking at it, you could tell some of the rock's story. Some rocks cooled so fast they have a glassy texture. Some rocks were filled with gas. So when they got to the surface, the gas all escaped and they formed a bunch of holes called vesicles. And those are formed by the gases as they come out of the solution. They come out of the magma. Just like opening a bottle of soda. All of a sudden, all this gas appears. So two types of molten rock: lava, liquid rock at the Earth's surface; magma, liquid rock beneath the Earth's surface. Do we care? Is there a difference? Well, the lava would have lost a lot of its gas, or most of its gas, and would also, if it's running along the Earth's surface, it would have incorporated stuff from the Earth's surface, so it's sort of impure. Magma, on the other hand, is coming up from deep below, would still have its gases and still have most of its what it was originally made of. So scientists can learn more from magma than from lava. So igneous rocks can have all these colorations. It could be light colored or dark colored or somewhere in between. So if we take a look at our reference tables, we, on the igneous rock identification portion, and I'll show you in a second, we see felsic. The term felsic means high in feldspar and silica. It's light in color and low in density. The other term is mafic, high in magnesium and ferric. That's where mafic comes from. These are dark in color, high in density. And here we have the amazing scheme for igneous rock identification. All right, this is awesome. So if we look at composition here, we see mafic and we see the metals in mafic. We see felsic, we see the metal, aluminum, in felsic. Right? Now it's important to understand that the rocks on the mafic side still have aluminum in them, still have silica in them, but they have more of the metal ions. So to read this, notice, all right, igneous rocks, we have two ways of splitting the igneous rocks up. The first is whether it's intrusive or extrusive. Intrusive, then, are all these rocks which would have large crystals. Extrusive would be all these rocks which would have either smaller crystals or just be glass, right? You could have just glass. So intrusive or extrusive are just based on the size of the crystals, and you could see those sizes given over here. But then we have to also consider which side of the graph. Are we on the left side or the right side? So on the left side, we see felsic rock, all right? We see felsic rock. So the way to read the graph is the composition will plot straight up and down here. So let's say we have a very felsic granite, right? So this granite is very felsic. Great. Well, you can read directly across and look at the percentages that you have here. You can see in here, this is about 50% potassium feldspar. Read from here about 20% to about 45%. That's about 25% quartz in here. Looks like maybe 10% plagioclase feldspar and maybe 5% biotite and maybe 2 or 3% amphibole. If you had a more mafic granite down here, you'd read straight up and down, and you'd see you have almost no potassium feldspar, more quartz, and you could read just to the side to get the percentages. You have quite a bit of plagioclase in that thing, some biotite, and some amphibole in greater quantities than they were in the felsic rock. A very felsic basalt would read on the felsic side of basalts. Okay, what do you have there? Well, a whole lot of plagioclase feldspar. Notice you have absolutely no potassium feldspar. So you have a lot of potassium plagioclase feldspar, a little bit of biotite, a little bit of pyroxene, well, actually a lot of pyroxene, and a fair bit of amphibole, right? If you become very mafic gabbro, well, you'd have very little plagioclase feldspar. You'd have a whole lot of pyroxene, and you'd even start getting the mineral olivine in there. So that's how you read this table, all right? Any rock will read straight up and down. If we have a mid-composition rock, these would be andesites or diorites. And what would be the difference? Well, andesite is extrusive, tiny crystals. Diorite is intrusive, very large crystals. So that is how you read this table. So to name igneous rocks, all right, well, if the composition is felsic and it has big crystals, that is granite. If it has big crystals and it's dark colored, mafic, that would be a rock called gabbro. Small crystals, but felsic, would be rhyolite, and small crystals and mafic would be basalt. And that is how you name those igneous rocks. When you make a thin section, grind the rock down so fine that light can pass through it, put it in a special kind of geologic microscope. This is just showing how large the crystals are in a gabbro. Similarly, in the same situation, you can see how tiny the crystals are in a basalt. So that is igneous rock. You can certainly tell when a place has had igneous rock placed on it recently. Pretty crazy.